A very good afternoon, ladies and gentlemen. How is the food? That's something I didn't wish to hear. Everyone happy? Tummy is happy? Yummy in tummy? But we can still be attentive throughout the session for 30 minutes. How many people have been working with machine learning or AI or are interested in this particular field? Wow, thank you so much for that. So today we'll be talking about machine learning and we are combining this with astronomy. Yes? Space lovers? Yes, thank you so much. Okay, so a lot of times when we hear the word machine learning, happens, right? But trust me, super easy, it's going to be fun, and I've tried my best to make it a lot of fun and not something that's going to go bouncer. Yes? Let's get started. So once upon a time, somewhere in 1947, Alan Turing said, what we want are machines. What we want are machines that can learn from its experience. Imitation game fans? Thank you. Well, here's another one. Computers today are able to see, hear, and learn. Welcome to the future. But before it gets to bouncer, hold on, we're not going to machine learning. Let's talk a little bit about astronomy first. 1 year ago, when I was browsing through the internet, I came across this really interesting video. It's actually a commercial, but it managed to motivate me. And today, as I talk about astronomy, it would be unfair if I do not involve this video as a part of my presentation. So let's first have a quick look at this video. It's going to be followed by a question. We still have Pixel? Pixel? दे रहा है ना? Okay.
अभी स्पीकर आया हुआ है, अंजलि तो बिजी हो गई यहाँ पर, दीक्षिता चाहिए। नहीं, उसी को वही करने के लिए बुला रहे, वहाँ से गायब है।
Oh, sorry. हाँ, मैं वापस से पे कर दूँ. But I just check it. हाँ.
My bag is there. Okay, just put it there. You are there, huh? Okay.
Still, sound is not coming. I'll play now. It's okay, I'll go ahead. So anyone who has worked in the field of astronomy here, or is someone studying it as a part of the academia? Anyone? No? I'll try my best to oh, yeah. Mind sharing your experience? Sorry, I couldn't hear you. Wow, from Kolkata? Nice. Thank you. हाँ वही वाला वीडियो हाँ. So the Greeks started this. They used to look at the sky and they used to wonder. They used to look at the patterns that the stars are making, and the word planetia comes from there. Planetia actually means things that wander. So that's how the word planet is derived. It's okay. Because we are connected and sharing. It's okay. It's okay. अच्छा ठीक है. So the astronomy compels the soul to look at the sky, and then as we look at the sky, we shift from one world to another. Yes? So what will happen if we were to fuse two of the most happening topics together? Magic? What happens when we mix astronomy with machine learning? Sounds interesting? Let's go ahead. How many of you all have heard the term exoplanets? Wow, thank you so much. So for those who haven't, exoplanets are planets that don't belong to our solar system. Yes? So a planetary system that is around another star, that particular planet is going to be called as an exoplanet. What we are going to discuss now is actually a project or a research work by Chris Chalou from the Google Brain team, and this is about detecting exoplanets in space. And we detect exoplanets in space using machine learning. Yes? Interesting? Okay. So what is the process of actually detecting a planet? Like any normal machine learning model, you'll have your data, you're going to train it, and then you're going to have your results. Yes? Or is it like astronomers just go out for planet hunting, like a walk to remember, just get on your suit and then go looking for planets? Does it work like that? Okay, let's see. Now imagine a star, yeah? So this is a star and this is a planet. And if you were a telescope and you are observing this particular thing, the moment this planet comes in front of the star, what is it going to do? Exactly. It's going to block a certain amount of light. Okay. So what we are going to do is that we're going to have our telescopes in space and we are constantly going to check for the fluctuations in the flux, the intensity of light. Yes? How is the intensity of light varying as the planet comes in front of a star and goes away? What do you think? What will the graph look like? If I were to plot a graph of time on the x and brightness or flux on the y, how will the graph look when a planet comes in front of a star? Perfect. It's going to give you a U-shaped curve or a V-shaped dip. Yes? Okay. Something like this, that's a star, and we see that a planet is coming in front of it, and there's a dip. And once the star is gone away, once the planet is away, then the brightness is back to normal. Yes? Easy? Okay. But can we sit observing each and every star that's there in space manually and then try to understand if it was a planet or not? Tedious, right? Let machines do the work. What we will do now is that we will take this data set, which are our light curves. So the first step of finding an exoplanet or having any machine learning model to work is our data. So the data is now figured out. My data is going to be light curves, which are having U or V-shaped dips. Next, what are we going to use? Convolutional neural networks. How many of you all have worked with convolutional neural networks before? Great. So what we do is that we give these particular graphs or light curves to the CNN model, and then it's going to predict whether it's a planet or it's not a planet. Yes? Okay. So the way humans see is something like this, which all of us are seeing. But when a machine sees an image, it sees it in terms of numbers. Yes? Okay. So we'll see what happens in CNN. Yeah? Familiar with this? Yes? Boring? Interesting? Difficult? Easy? coffee? Okay. So in the first image, what we see is that you have selected a window, which is going to be, your window size can be altered depending upon your data, and then it keeps on shifting. Okay, so here in the example, you can see the window size is 3 by 3 and the stride is 1. The example in this particular one. Okay, what we are going to do is we can do max pulling, or we can simply do pulling, where we take out or try to minimize or reduce the size. So over here in the example, single depth slice, what I have shown is max pulling. So in the numbers 0, 1, 4, 6, the greatest number is 6. So we take that and then go ahead the similar way and you get your next step. Yeah, so there are many layers. So what happens when this was moving and it's come to an end, but we have not managed, so if it's not fitting in your window size, what will you do? Give a 0 padding. Yes? So that you can scan further. Helps? Okay. We create filters to detect these U or V-shaped dips. Once you've created the filters, you're going to do convolution. So it's basically nothing but you're going to multiply and you're going to then add them. In case if your filter matches your data, in that case, we're going to have a very large number. In case if it's not the case, then it's a 0. Yes? Difficult? Okay. So basically a CNN will have many layers, and the data is pushed forward, where at every layer some data is rejected, some is carried forward, and in that way you just go step by step. Yes, you go step by step and then you'll be getting your final results. So this particular model, now that we've seen, we want to know how valid it is. What's the accuracy that this would give if we go ahead with this, right? Well, you can see this, there's a snippet here, and the accuracy that was given by this model was 95%. And something very interesting is that this model did not just predict 3,000 new planets. There are many planets in the habitable zone, which means that it can support life. But even if we were to take Falcon Heavy, which is the rocket we can travel in, the amount of time that we would take to go from Earth to that particular planet, it's way more than the human lifespan. Difficulty here. But anyways, Kepler 90I was the new planet that was found, and after which the Kepler system became the next largest planetary system. So our solar system has how many planets? Okay, and the other stars, we have managed detecting a planetary system which is about like 2 or 3 planets around it, but the next biggest one after us is actually the one which is rotating around the Kepler star. Yes? Interesting? So a few fun facts about the Kepler 90, it's 30% larger than the planet that we are living on, so it's 30% larger than the Earth. The surface temperature is somewhere around 800 degrees Fahrenheit, which is not supporting human life. And other than that, it orbits after every 14 days, which is a good point because you can celebrate your birthdays after every 14 days. The exact distance, I don't know the number, sir, but I will probably Google it and tell it to you. Yes, no, not me, the same thing. It was open sourced and a lot of developers were working on this particular project. So this particular thing was actually detected by Chris Chalou, and that is when the model started getting a lot of popularity in the developer community, and then it was made, so people started contributing towards this. So for a long time, and to be very honest, human life, it is staggeringly interesting because the way a ball of rock will rotate around a fireball in complete dark vacuum, and how nature's law conspired to create a naked ape that would stand on these rocks, look at the sky and go. Yes? But ladies and gentlemen, the universe is under no obligation to make any sense to you. Thank you.